Well, hello there. Hello there. My name is Dr. Alex Baker. There's going to be lots of puns, guys. I'm a research chemist and academic at the University of Warwick, and I unashamedly love Star Wars. I first remember... Yeah, go on then. I first remember watching Star Wars on my dad's old VHS tapes. For those younger members of the audience, we had that before DVDs, and that was also what we had before YouTube as well. So it was a fair while ago. And since then, I've been absolutely hooked. And like every person who loves Star Wars, I always dreamed of being a Jedi or a general or even a politician, swanning from planet to planet, saving the day. Realistically, though, in a galaxy that contains billions and billions and billions and billions of people, this isn't really attainable. There aren't many Jedi or generals, and thankfully, politicians. So to solve this problem, I went away and looked at the job of a Jedi and listed the perks and the privileges of the role. And I came up with a few things. The ability to travel for work, a good salary, job security, the ability to have an impact, and, of course, unionized, whether that be in the Techno-Union or the Jedi Order. And if you take that long list of criteria and look around the galaxy, you're really left with one solution: bounty hunting. It has all the benefits of a good salary, travel, and job security, and you make an impact. Consider Boba Fett. He had money coming in from the Empire and from Jabba the Hutt. He has his own ship, and of course he now has his own spin-off. That's job security. He was also unionized as well, right, in the Bounty Hunters Guild. That would protect his job. What more could you want? So I think the most logical thing for all of us to do this evening is become bounty hunters in the Star Wars universe. Therefore, and I haven't told the RI this, my talk tonight isn't actually entitled The Chemistry of Star Wars. It's entitled How to Be a Star Wars Bounty Hunter. Now, as a bounty hunter, you're going to need a few things to get your business started. And it's going to involve a little bit of traveling around the galaxy. The first thing you're going to need is a weapon. Now, there's a smorgasbord of weapons in the Star Wars universe: Wookiee bowcasters, Stormtrooper E-111, blasters, and iconic lightsabers. So let's take our first trip into the Star Wars universe. We're going to go to Coruscant, the capital planet of the galaxy. All hyperspace routes lead here. You have the Jedi Temple on this planet and the Senate on this capital planet. Fortunately, as a bounty hunter, there is also a seedy underworld ready to sell you weapons on the illicit market as you start off your novice bounty hunting business. So I want to start with a question. Are blasters in Star Wars laser guns? Yes or no? So we're going to do a hands up. Are blasters in Star Wars laser guns, yes or no? Who thinks yes? They are laser guns? Who thinks no, they're not laser guns? So the answer is no, they aren't laser guns. Take this fine example of a DL-44 heavy blaster pistol from Blast Tech and famously sported by Han Solo. Now, the key component of this weapon is its gas canister that contains Tabana gas that we're going to come back to later on, and a power pack. Now, what happens when you pull the trigger is a burst of gas is released from the gas canister, it's ionized and then fired out the end as a shot, which I've shown here, using xenon as the gas. Now, in scientific terms, this weapon shoots plasma. Plasma is the fourth state of matter after solids, liquids, and gases. Plasma is known as an ionized gas, where the electrons have been separated from their atoms. You have free electrons and cations floating around. The state is known as quasi-neutral. You have the same amount of negative charge as you do positive charge. They're just not combined together in the atom. And you see plasma in lightning and stars and solar winds with temperatures exceeding thousands of degrees Kelvin. And we can replicate that today. We can make a Royal Institution blaster. So the first time, please welcome the demo team. And if you look around your legs, there should be a very long pipe. And what I'm going to do is this. So that hissing noise you hear is me filling the pipe with flammable gas. Don't worry, though, you are all perfectly safe. So I'm going to fill my pipe with flammable gas. We're going to come back to flammable gases as fuels later on in the talk. But for now, I'm going to wait for my colleague to tell me if he can smell gas. Excellent. So here we go. Ready? 3, 2, 1. So there we have our plasma going round and round and round and round and round and round and round our pipe. Excellent, guys. Please put that back down for me. So what we get is a blast like in Star Wars. So in Star Wars, people are not firing light at each other. They are firing superheated ionized gas, which means because plasma has mass, you can stop it with the Force, which means this highly controversial scene from The Force Awakens is actually possible, although I still don't think being very good films anyway. What if you don't want a blaster, though? What if you want something more civilized? Let's head to the planet of Ilum. So this is a small, snow-covered planet where we can get a key component for your lightsaber, a more civilized weapon for those of you looking for some elegance in your bounty hunting. Now, like blasters, lightsabers are not laser weapons. Inside your lightsaber, you have a power pack and some crystals. What happens is a laser passes through the crystals, it is focused, it reaches the end of the blade, and it then ionizes the air at the end of the hilt to form a plasma. The plasma is then held in a magnetic field to keep its blade shape. The problem is having a magnetic field that is a straight line, as you will effectively make a fountain of plasma as the field gets weaker and weaker and weaker as you move away from the source of your magnetic field. Now again, if we use xenon gas as an example, near the hilt where the magnetic field is strongest, we can maintain our plasma. But as we move away from the hilt, if you aren't continuously maintaining that plasma, our electrons and our cations are eventually going to recombine. Now, in Star Wars, this problem that breaks the laws of nature is overcome with the Force. So while I can't show you a lightsaber, I can show you what a blade might look like if uncontrolled and controlled in a magnetic field. Let's start with the uncontrolled. And this can be demonstrated with this piece of equipment here, which is known as a Tesla coil, of course invented by Nikola Tesla, who I think bears a striking resemblance to a young Count Dooku. Now, in simple terms, a Tesla coil works by forcing a buildup of electrons in the coil and the toroid, and that is then released into the air in the form of a plasma. And we're going to encourage this further in a minute by providing a second wire to this, but I'm not going to talk about that yet. I'm going to step back a bit, and Michael is going to increase the power.
Okay, enabling.
So we are now driving electrons into the coil and the toroid, and you will see at the end of that wire there at the very top, if we can have the lights down just a tiny bit, we can see our uncontrolled plasma. I'm going to leave you with that for one moment. AV aren't going to be happy otherwise. Oh, perfect. You may notice that there's a striking resemblance to Force Lightning as carried out by Darth Sidious and Count Dooku, which is what we're going to try now. The plasma pipe back down to the front, that will be incredibly useful. And if I can hand that to you guys, this is the problem with wearing chainmail. Perfect. So we see uncontrolled plasma elsewhere in the Star Wars universe. It falls lightning by our pistol. I like to think of that like sometimes. Magnetic field, though. So, here I have a glass ball containing xenon gas. And what I'm going to do is I'm going to apply a magnetic field across the glass ball. And if we can have the house lights down ever so slightly, that would be excellent, please. So, where's the switch? There's the switch. Here we go. So I'm going to turn on my magnetic field. There we go. So that is xenon gas, ionized, held within a magnetic field. And this is what a lightsaber blade would actually look like. And it is this principle that underpins nuclear fusion reactors currently under development around the world. There you go. But where did the colors of the blades come from then? Well, in Star Wars, the colors come from the Kyber crystals taken from planets such as Ilum, and the color produced is based on the Jedi or Sith's interaction with that crystal. So we have the classic blue of Jedi Guardians like Obi-Wan, we have the green of Jedi like Yoda, and the red of the Sith. Or if you're Samuel L. Jackson, who plays Mace Windu, and you want to stand out in the film, you, of course, pick your favorite color, that is purple. But the color comes from the wavelength of light emitted by the lightsaber. So Mace Windu's purple lightsaber is actually a higher energy than Darth Maul's red lightsaber, because purple is a higher energy and shorter wavelength compared to red. On an atomic level, what is happening is photons are being produced by exciting electrons to higher rungs of our energy ladder, and then those electrons slowly relaxing back down and releasing photons as they go. So in the case of purple lightsabers, electrons are losing energy in larger increments than red lightsabers. What is more interesting from a chemist's perspective, though, is that different elements give out different colored photons. So the color one element emits will be different from another. And I can show you this not by using a plasma, but by using flame tests. We can heat up elements using a flame, giving their electrons lots of energy, and then as they relax back down, they will give out that energy as light. And we're going to do this with a bit of a game. I like to call Sith or no Sith. So the demo team are going to spray a certain element into a Bunsen flame, and you have to predict if it is a red flame, that is Sith, or anything but a red flame, that is no Sith. Here we go. So the first element is lithium. Do we think Sith? Hands up for Sith. Hands up for no Sith. Off we go. So it is red, so it is Sith. Our second element is sodium. Do we think Sith or no Sith? Hands up for Sith. Hands up for no Sith. Here we go. It is orange, so it is no Sith. The third element is boron. Do we think Sith or no Sith? Hands up for Sith. Hands up for no Sith. Boron it is then. So boron is green, so it is no Sith. Our fourth element is strontium. Do we think Sith or no Sith? Hands up for Sith. Hands up for no Sith. Strontium it is then. Strontium is kind of a reddy, violety color that I'm going to call Sith. The final element then, our fifth element, cesium. Do we think Sith or no Sith? Hands up for Sith. Hands up for no Sith. Here we go, cesium. So it is a purple color that I think Samuel L. Jackson would be proud of. So it is no Sith. Round of applause, please, for our demo team. The ability to identify elements based on the photons they emit is incredibly useful. It is used to identify elements by simply looking at them. If we look at this star, so we can look at the emission of stars and we can see what elements they contain. So this star we know contains both hydrogen and sodium because it contains the emissions of hydrogen and sodium. So those flame tests we all did in school really do have interstellar applications. So we have our weapons, be it a blaster or a lightsaber. You're all one step closer to becoming a successful bounty hunter, as you can now shoot things. However, what's to stop you from getting shot? Let's go to our next destination, that is Camino. Now, why have we come here? Well, we can get ourselves some nice, shiny, white armor from the home of the clone troopers. And with a little bit of research, we can find out that the armor worn by clone troopers and stormtroopers, and indeed TIE fighters as well, is a white plastoid. Now, there is no such thing as a plastoid, but we can make a reasonable assumption that it is probably a plastic. That means it's a polymer of some kind. Now, polymers are repeating chains of smaller units known as monomers. You can think of them like Lego bricks when assembled together in a long chain. A common monomer would be something like styrene, that when put into a chain becomes polystyrene, a chain of styrene. And there are a few options then that you could look to for your armor. In real life, the cosplay outfit of clones and stormtroopers is made from ABS plastics, as you can see modeled by our amazing volunteers. Now, these plastics, ABS, are a combination of these three monomers, acrylonitrile, butadiene, and styrene. And they're relatively strong and easy to manufacture. The plastic is normally white, hence the classic white armor of stormtroopers. And we use ABS for a huge host of things, from keyboards to cosplay outfits to Lego bricks to 3D printing. But it isn't fantastic at stopping a bullet. So as prospective bounty hunters, may I suggest a different polymer? Polyethylene, perhaps, a polymer of one of the simplest monomers, ethylene. Now, you may think this is stupid. Polyethylene is found in plastic bags. Surely it won't stop a bullet. Well, I have a question for you. What is polyethylene used for? Plastic bags, ropes, chopping boards, or hip replacements? So if you think polyethylene is used in plastic bags, put your hands up. Excellent. Half of you are paying attention. Wonderful. Better than my undergraduates. Rope. Anyone for rope? Chopping boards. What about hip replacements? Excellent. So polyethylene is, in fact, used for all of those applications depending on its density. We use lower density polyethylene for applications like plastic bags, but high density polyethylene for applications like body armor, which means, in theory, and let me stress the in theory bit, you may have a chopping board at home in the form of high density polyethylene that, in theory, could stop a bullet, if combined with a few other things. Please do not try using your chopping board at home to stop a bullet, because we have tried it here. So in this video, we have an air rifle, and we have an ABS Lego figure, we have a low-density polyethylene plate, and we have a high-density polyethylene chopping board. And that chopping board is this one here. And that little dent you can see there, I put some black paint in it so you can see it a bit better. That little dent is all the air rifle did. Why? Well, the reason a plastic bag can't stop a bullet is because of the way the polymer chains in low-density polyethylene packs together. In very low-density polyethylene, we don't have nice packing chains. We get an awful lot of branching. This means the chains cannot pack very effectively together, leading to gaps and making it very low density. In high-density polyethylene, we don't get that branching. We get very nice linear chains that pack incredibly effectively on top of each other. And this is important because we get very good packing, but we also get what's known as intermolecular forces between our chains, attractions between our chains. It's the same principle behind having two phone books and overlapping them and trying to pull them apart. And these intermolecular forces form instantaneously. What happens is some electrons in one atom sway to one side. That makes a little bit of negative over here, a little bit of positive over here. That pushes some other electrons over, and we get a little bit of attraction between our chains. So not only do you have really good packing, but the polymer chains themselves are very weakly attracting each other using these instantaneous intermolecular forces. The question is, can we go one better? Can we replace these very weak instantaneous intermolecular forces that come and go and fluctuate? Can we replace them with something more permanent? To answer that question, we need to travel to Malastare. Now, Malastare is the home of the Dugs, think Sebulba from episode one. They are a rapacious species determined to take all the oil riches from their planet. But they are not alone on that planet. On their planet, there is also a very rare species of animal known as zillobeasts. If you're a proper Star Wars nerd, you know what I'm talking about now. Now, the zillobeast is a gigantic lizard-like creature, a bit like a Star Wars Godzilla. And in Star Wars, the idea is put forward by the Republic of using the scales of this beast to make better armor. Now, this might sound far-fetched, but during certain ceremonies, Roman soldiers would wear the skin of crocodiles as body armor. So here is an example from the British Museum of some Roman armor made from a Nile crocodile. So using zillobeast skins to block blaster fire might be a good idea. But why? Well, keratin is a biological polymer found in everyone here's human hair and nails. It's also found in a different form in lizards and birds. And what you have in keratin in lizards and birds are very long chains of repeating amino acids, the monomers of proteins. And these amino acids can form very strong permanent forces across chains. They do this with their slightly negative oxygen and a slightly positive hydrogen on another chain. And unlike polyethylene that only has these very weak instantaneous forces that come and go, crocodiles and likely zillobeasts have these much stronger hydrogen bonds in their armor. And I can demonstrate to you how strong these hydrogen bonds are using some paper. Now, you all, of course, know that paper is made of cellulose, another natural polymer, but this time derived from trees. Now, between the chains of our cellulose, you have hydrogen bonds. Which camera are we on, guys? That one. Let's go this way a little bit. So what I have here are 2 bits of paper. I'm going to attach weights to the bottom of them. And if I disrupt the hydrogen bonding in my cellulose chains just with water, so just providing some more hydrogens and oxygens, what you will see is eventually, he says, this one should break. Yay, excellent. Okay, what we have done is we've disrupted the hydrogen bonding in our paper. We've disrupted those very strong bonds. In here, I just have acetone, otherwise known as propanone. You might use it to clean things or take nail varnish off your nails. It's just an organic solvent. If I spray this onto my sheet of paper, I'm very confident that paper won't break, because I'm not disrupting the hydrogen bonds in any way. In summary, hydrogen bonds matter. You as a bounty hunter want them in your armor. Unfortunately, there are a limited number of crocodiles on the planet, and there are a limited number of zillobeasts in the galaxy. So I would suggest it would be slightly unethical to skin all the crocodiles or skin all the zillobeasts to further your own bounty hunting business. Don't worry, though, because chemists have the solution, and it's this stuff. It's called Kevlar. It was developed by DuPont in 1965 to replace steel in some applications. And it involves these 2 monomers here that are hydrogen bonded together across the chains. And it is an exceptionally strong material. And it's all thanks to this amazing woman, Stephanie Kolek. So she not only invented Kevlar, she also invented the nylon rope trick, and she helped make nylon as well. She was a truly amazing woman who pioneered material science. Her Kevlar inventions have been used in spaceships, satellites, phones, planes, and bulletproof vests. And pound for pound, Kevlar is 5 times stronger than steel. But it won't stop a lightsaber. we ideally want a material that can stop a lightsaber and blaster bolts. We want what the Mandalorian wears, in which case we want to go to Mandalore, the home of the Mandalorians. Now, the Mandalorians have always mistrusted the Jedi, so have developed a material to protect themselves from lightsabers, and it's this material we want to get our hands on. Beskar, also known as Mandalorian steel or Mandalorian iron, is a metal. From a chemical perspective, this means we have a load of positively charged metal ions sitting in a sea. This is quite, what, they do this every year, guys. They always intimidate me behind my back whilst I'm speaking. That can move between them. In this way, Beskar is more like steel, an alloy of iron and carbon, rather than something like Kevlar, that is just a carbon-based chemical. Now, it's the attraction between the iron cations and electrons moving between them that gives steel its strength, whilst it's the carbon that provides the steel its rigidity. This is different from Kevlar, that is only based on those carbon, hydrogen, oxygen structures. The only problem, though, is while metals are good at dissipating heat, if I start waving a lightsaber around you and you're just wearing steel, you will notice it. We know that lightsabers are made from a very hot plasma, thousands of degrees Celsius. I've shown that to you already. And steel armor is simply not designed for that. This is because while steel is good at dissipating heat, the mechanism it uses of one cation vibrating and one cation vibrating and that vibrating another, and that dissipating the heat, is not the best way to do that. So I can demonstrate that to you. Here I have a block of ice. So with this block of ice, I'm going to try and cut it with this steel disc. And what you will see is I don't get very far into the ice. The heat from my hand does not pass through my steel disc particularly well. But I have this material here, which is much more effective at cutting through the ice. I can leave it sitting in there. That material there cuts ice like butter. And that material there is a very special material made by Professor Julie McPherson's lab at Warwick. It is synthetic diamond. Whilst steel transmits heat by that little vibration, the carbon atoms in diamond are far better at transmitting heat. As soon as one vibrates, another one vibrates near instantaneously. And we use synthetic diamond in a variety of applications, from heat-sinking applications to, may I suggest, using it in your Mandalorian body armor as well. So you have your weapons and you have your armor. It's time to find a ship and some fuel. Can we get a round of applause for our Mandalorian? That was my way of hurrying him off the stage before he kept intimidating me behind my back. So let's go to our next planet. Let's go to Bespin. And Bespin is the ideal place for ships and fuel. This gas giant is rich in a fuel used to power most ships, from Star Destroyers to Millennium Falcons. And in Star Wars lore, there are many, many, many different kinds of fuels that are available. You have Rhydonium, you have Kesselin, you have Malastrian fuel, and Nergon-14, found in spaceship wrecks on the planet Jakku. But the main fuel is Tabana gas, found in the atmosphere of planets like Bespin. And it's this gas that made Lando Calrissian rich and was used to freeze Han Solo. Helpfully, it's also a waste product from creatures called Beldons, a bit like how methane is a waste product from cows. To a chemist, then, it's likely that Tabana gas is a hydrocarbon, an organic chemical consisting only of hydrogens and carbons, like fuels such as petrol. To burn our fuel, though, we need oxygen and some heat. And what we find is that the larger the hydrocarbon, the longer the hydrocarbon, the more carbons and hydrogens it contains, the more energy per molecule of combustion we get. And this raises the question, why aren't rockets powered like intercity trains using diesel? Well, it isn't just about producing lots of energy per molecule. It's about how much thrust you can make based on weight. And it's this kind of chemistry that underpins rocket science. And in rocket science, the concept is called specific impulse. This is the amount of momentum you can produce per kilogram of fuel. This means that very light fuels like methane are better in rockets as they have a lot of energy and they're also incredibly light. They have a high specific impulse. But it's not just the fuels you want, you also need oxygen. And I can demonstrate that to you here. So what I have here is some ethanol. So have you guys got the ethanol one for me? Perfect. So whilst they're sorting that out, what I'm going to do, gently behind Dr. Sargent's back, is light some ethanol. And you can see that ethanol burning. And to burn, that ethanol requires oxygen. For every molecule of ethanol I burn, I require 3 of oxygen. However, the only oxygen this ethanol has is coming to it from the atmosphere. What if I provide another source of oxygen then? Well, to produce lots of oxygen, I'm going to use the reaction of potassium permanganate and hydrogen peroxide that hopefully you guys have already put in there. Excellent. So let's light this one. Is it going to light? No. Might have to squeeze round. Sometimes it needs a little bit of a kick with my favorite thing, ethanol. So let's just pour a bit more ethanol in there. If I light that, there we go. So, much more oxygen. It will be quite loud, so do cover your ears. So what I have done is by reacting potassium permanganate with some hydrogen peroxide, I have produced a lot of oxygen on demand. I can therefore burn my ethanol far more quickly in this much more violent reaction. So in rocket engines, we not only need fuel, we also need oxygen. So in some rocket engines, we might combine methane and oxygen in high concentrations and burn vast amounts of them to produce thrust incredibly quickly. It's the fire triangle, right? Oxygen, fuel, heat. But if you wanted to store enough methane and oxygen at room temperature as gases, you would require huge and incredibly heavy storage containers. The solution then is to use liquid oxygen. So oxygen becomes a liquid at about negative 183 degrees Celsius. Can I grab them? Perfect. So what we have here is some liquid oxygen. So this is, yeah, I'll do it in there. This is liquid oxygen. If we allowed it to expand, 1 milliliter of this as liquid oxygen would expand 860 times to become almost a liter of gaseous oxygen. Now, for years, the thought that you could have liquid oxygen was considered absurd. So very illustrious fellows of the Royal Institution, such as Michael Faraday, would term oxygen a permanent gas because he believed it could never become a liquid. It would require James Dewar to show it and fortunately make Dewar flasks for us. So what I have here is some wonderful treats that if I try and light without any oxygen, you will see nothing happens. However, get the sand ready. let's not do it with the one I've already slightly charred, just in case. If I provide some liquid oxygen to this, give it a good old dose. You guys got the blowtorch for me? There we go. So that is what happens if we provide more oxygen. So that, go on then. Is liquid oxygen. Now the problem with, it's not very difficult to make liquid oxygen if you're in a very well-equipped lab space, such as the Royal Institution. However, storing it and transporting it at very low temperatures is incredibly difficult. And to illustrate this point, what I have here is a map that shows how difficult it is to transport certain things at certain temperatures around the world. And you can see as we start to drop the temperature, how much more difficult it becomes to transport materials at negative 60 degrees C. And we need to go far lower for liquid oxygen. And this isn't just a problem for liquid oxygen. This is one of the main reasons why it's difficult to get medicines and vaccines around the world. This is why it was so hard to roll COVID-19 vaccinations out around the world. We couldn't transport them very easily at low temperatures. And it's a problem that my own research group hopes to overcome as well, as we study neglected tropical diseases and different therapeutics and diagnostics for those diseases. But in the Star Wars universe, there is a solution. Carbonite, used to freeze Han Solo and store fuels at low temperatures. Now, carbonite does not exist in the real world in the same way as in Star Wars. If you say carbonite to a chemist, they will probably think of an ion of carbon and oxygen together, or they will think of an early explosive that contains nitroglycerin. In the Star Wars universe, though, carbonite is a metal alloy that contains carbon, much like steel. But it can also be used to trap gases such as Tibanna gas. Now, it turns out this is actually a really good idea. It's an easy way to store and transport a very useful fuel. So in the real world, we have moths. Now, these are not high-ranking imperial officers, but metal organic frameworks. Imagine a honeycomb where the walls are made of metals separated by long organic chains. And if you're very clever, what you can do by changing the composition of your moths, by changing the metal and the organic chemical, is you can make a porous material that can capture other chemicals. And what scientists have done is make moths that can hold hydrogen gas at much lower energies than in a cylinder. Now, this is the technology that will probably make hydrogen-powered cars possible. Why hydrogen, though? Well, while other fuels like Tibanna gas, methane, and petrol produce carbon dioxide, burning hydrogen and oxygen only produces water. Hydrogen also has an excellent specific impulse. You literally get a lot of bang for your buck if you can store it properly. Now, one way to make hydrogen rapidly is, of course, to use the reaction of sodium with water. And that reaction can be quite loud. So again, if you would like to cover your ears, please do so. Excellent. So, can I squeeze behind that, please, Fergal? So, what I have here is a small tub of some boiling water, a small amount of sodium. I'm going to combine the two together. We're going to produce hydrogen very rapidly. Demo team, can I have some safety specs, please? Look at this. Giving his own eyes for the greater good. So, I'm going to combine my sodium with my boiling water. So, There we go. So that is a very violent reaction producing a huge amount of hydrogen incredibly quickly that then catches fire. So in this reaction, all we are producing is hydrogen gas that then burns in air to just produce water. Now, sodium is used as a fuel in Star Wars. We don't really know what for. Maybe it's used to produce hydrogen from water. We really don't know. So you now have your weapons, you have your armor, and you have fuel for your ship. In my mind, you are one step away from being a Star Wars bounty hunter. We just need to talk about how you're going to store your target and bring them back alive. Now, fortunately, we've already discussed the use of carbonite to store fuels at very low temperatures, but would it actually be possible to freeze a human? And for me, there really are two key questions. Can you store an organism in a solid metal like carbonite and have the person survive? And can you lower a human's body temperature to below 0 and have them survive? To do the first, we have to have a metal that is a liquid at near room temperature. After all, we don't want to fry you as soon as we chuck you into this vat of molten metal. Now, there are only a few metals we can really do this with. There is mercury, which is highly toxic. There is cesium, that reacts even more violently with water than sodium, so we're not going to use that one. Or there is gallium. Now, this may seem like science fiction, but there have been a few studies with a few small worms called nematodes have been dehydrated and then frozen in solid gallium. Now, once removed from the gallium, they are then rehydrated and live happily. Now, I'm not suggesting that this is going to be the solution to how we do this to human beings, but the concept is there on very, very small scales. And again, we're not going to freeze humans or worms because that would, well, frankly, be highly unethical to do, and I don't want the university for that. But we can show you how easily gallium, a solid at room temperature, can be turned into a liquid by simply taking it above gallium's melting point of 29.7 degrees Celsius. So what I have here, for those more eagle-eyed of you, is my little gallium solo that I have frozen in gallium. And what I can do is I can take up poor Han's body temperature to above 30 degrees Celsius. Now you can see how easy it is to melt my gallium solo. The real question, though, why do you want to do this? Why do you want to freeze Han Solo in the first place? Well, the answer to that question, and building on my extensive experience in university governance, I've done a SWOT analysis. Now, for those of you who are too young to know what a SWOT analysis is, it's a bit of quite pointless paperwork that corporations sometimes get their employees to do. So why freeze Han Solo? Strengths. He can't run away, and Jabba likes it. Good. Weaknesses. He might die, and cryogenics, as we've discussed, are quite expensive when we talk about freezing fuel and liquid oxygen. Opportunities. Han Solo makes a fantastic wall hanging for Jabba's palace and my ship. Threats. Han Solo might die, and Jabba wants him alive. So why does Star Wars have this technology? Well, if we want to travel beyond our own solar system, so go interstellar, we need this technology. Our nearest star is Alpha Centauri, just over 4 light years away. So I have a question for you. How long would it take to get to Alpha Centauri with current technology? So if I stuck you on NASA's launch pad today, pointed you at Alpha Centauri and lit the fuse, how long would it take to get there? So, if you think 6 years, 60 years, 600 years, 6,000 years? The answer is 6,000 years. And this is a massive challenge for the future of humanity that we need to overcome. It's the same challenge that the people in Star Wars needed to overcome before hyperdrive. Now, if you wanted to travel interstellar, i.e. travel across a galaxy, not just a solar system, you need this technology to help you extend the lifespan of your travelers. You need this technology to have a galaxy far, far away, not just a solar system nearby. How does it work, though? Well, hopefully, here I have 2 beakers, both containing sodium hydroxide. Have I got my beakers, please? So, in a moment, imagine there are 2 beakers here. They are both going to contain sodium hydroxide and a little bit of indicator solution. And what I'm going to do is I'm going to add some of this stuff to each of them. Now, this stuff is dry ice, solid carbon dioxide. And what's going to happen when I add these 2, have you got a spatula I can borrow? There we go. We'll get to that later on. So what I have here is I have a beaker of relatively cold water with some alkali solution, is it? And some universal indicator in. And what I'm going to do is I'm going to add a small amount of my dry ice to that one. And then I'm going to add a small amount of my dry ice to this one, which is much, much hotter. Now, in this reaction, what we are doing is we are adding CO2 that's going to dissolve. It's going to become carbonic acid. It's going to neutralize our base, our alkali solution. And then what you're going to see is there should be a color change. You can just start to see the color of this one ever so slightly changing. Now, what you can see here is that the faster we do a reaction, the higher the temperature, the faster a reaction occurs. So in this case, this reaction is going much faster than this reaction here. And you can do the reverse as well. If you cool down a reaction, you can slow down a reaction. And this is going to be key, and we're going to apply it to humans. So my question to you then is, how many chemical reactions occur in your body every single second? 1 million, so that is 10 to the 6, 1 billion, so that's 10 to the 9, 10 to the 15, or 10 to the 22. And whilst you're thinking about that one, what I'm also going to do is I'm going to pour some liquid nitrogen into here, and I'm going to add my former spatula, now banana, into there. And we'll get to that in about 10 minutes' time. So, how many chemical reactions occur in your body every second? 1 million. Who's up for 1 million reactions? What about 1 billion reactions? 10 to the 15 reactions? What about 10 to the 22 reactions? So the answer is 10 to the 22 reactions. And we get to that number by estimating the number of reactions per cell per second is about 1 billion, and we multiply it by the number of cells in your body, and we get to about 10 to the 22. And this is a vast number. It's just under the number of stars in the known universe. And this is a written representation of some of those reactions. And you can see just how incredibly complex they all are. And if we zoom in, you can see in more detail that complexity. You are all amazing examples of why chemistry matters and why chemistry works. The aim then is to cool someone down, to extend their life and also decrease the amount of food, water, and oxygen required when they're in space, so the less fuel we need to put them in space. And NASA have been exploring this concept for many years now and have got to about 32 degrees Celsius. The aim is to cool a human body down, reduce the number of reactions occurring per second, reduce the amount of energy needed, the amount of oxygen, the amount of food. The idea has been fairly well shown in goldfish. So again, please don't try this experiment at home. But what scientists have done is they've taken a goldfish and they've slowly lowered its body temperature. And what you can see there, that line going down, is the number of reactions, it's the metabolism and respiration of that goldfish. So the colder the goldfish, the fewer reactions that are occurring in that goldfish, therefore less food and oxygen the goldfish requires. Why are we so interested in going sub-zero, though? Well, at room temperature, this piece of rubber is nice and stretchy. However, if I start to cool it down, we'll get to that in a minute. If I start to cool this down in the liquid nitrogen, what I can do is I can remove all the energy from all the polymers and all the molecules in the rubber until it becomes exceptionally solid. So that end is still warm and stretchy. That end is incredibly solid. However, it's not really a biological solution, is it? So what I have here is a biological solution. A chicken egg. And what I can do, let's see how good I am at Gordon Ramsay one-hand breaking an egg. Here we go. Ish. So here I have my chicken egg. And what I'm going to do is I'm going to add some liquid nitrogen to my egg and give it a nice Gordon Ramsay swirl. So what I'm doing is I'm lowering the energy of all the lipids, of all the molecules, all the proteins, the cell membranes, the sugars, everything in this egg. I'm lowering the energy. I'm taking all that energy out of the system by lowering the temperature. Decrease the temperature, decrease the number of reactions, decrease the energy. Until what I'm left with is a fried egg. What I've done is I've taken all the energy away from it. If I leave that here until the end of the talk, and maybe about 20 minutes after the talk, what you'll see is it will just defrost again. But you know what the biggest problem is to going sub-zero with a human being and therefore freezing Han Solo. It's ice. So you remember that banana we froze earlier on. If I can just get some boiling water from the demo team, what we're going to do is we're going to take our frozen banana. Thank you. Let's put some boiling water in there. We're going to take our now very frozen banana, and it will be exceptionally cold. I'm going to put it in some boiling water. And we're going to come back to that in about 2 minutes. Because what happens when you freeze and defrost things is as you freeze, you can see our ice crystal there growing, getting bigger and bigger and bigger as we freeze our cells. And this starts to cause stress and damage on the proteins and cell membranes in your cells. This means that when you freeze and then thaw your cells, they all start to leak and become very damaged. And you observe this when you put raspberries in your freezer and then take them out and defrost them. They go all squishy. All that structure the cell has been ruined by ice. And when refreezing ice cream, that grainy texture that no one likes is ice crystals growing in a way we don't want them to happen. It's all because ice crystals are growing. Which is why, kids, when your parents tell you, put the ice cream away, you've had too much, the answer is no, because if I do that, ice crystals will grow uncontrollably and it won't be so nice. So you just have to eat it in one, unfortunately. And we can also see this in our formerly frozen banana. So what we have here is our banana that we have frozen in liquid nitrogen, and now we have defrosted. And what you can see, if I just run my hand over it, you can see it's gone all gloopy and horrible. All the cell membranes, all the protein structures have been damaged by that ice growth and that ice thawing. Hence, if you did actually freeze Han Solo, Jabba would be deeply annoyed, as Han would become a pile of mushy cell detritus on the floor. That was a risk, right, or a threat in our SWOT analysis. So we can't even freeze bananas, raspberries, or really ice cream properly. So the idea of freezing blood, organs, and cells, or Han Solo, is so far off. And this is a massive problem, not just for the future of humanity in space, but here and now as well. It's a problem because currently we can't effectively freeze blood from blood donations very effectively. This means that we constantly need more and more blood donors to donate blood, and we're only ever a really serious health crisis away from running out. And we can't freeze organs either. So thousands of people sit and sadly die on waiting lists waiting for organs. Statistically, one person in the UK dies on the UK organ donor list every single day. So the problems of freezing Han Solo has real-world impacts in the here and now. And this is where the research of some of my colleagues comes in. So this is Professor Gabriele Soso from the University of Warwick. And what you can see are some small molecules we can use to control ice growth on a molecular level. So what we have are two similar chemicals, one that slows ice growth and one that does not. So these are two real computational simulations. The top one shows that little kind of cyan chemical controlling ice growth. It stops ice growth. This bottom one, a similar but different chemical, gets overtaken by that growing ice. Real computational simulations showing how we can control ice growth. And as researchers, we look to nature for inspiration in how to solve this problem. And there are loads of organisms that live in very cold climates that have specialist antifreeze proteins to help themselves control ice growth in their blood and organs. And my favorite example of this is the North American wood frog, I like to call the frogsicle. So in this video, we have a frog that can survive freezing. So its body has been entirely frozen over winter. We've now reached spring, and it is starting to defrost. We have animals that can survive extreme cold and ice formation, and as scientists, we are trying to mimic them to save lives in the health service, and in the long term, make interstellar travel possible, like in Star Wars. So in our galaxy, do we currently have the technology? No, but in Star Wars, they clearly do, and my hope is that some of the younger members of this audience will go on to really change the world by carrying out that research and making it possible. So you have your weapons, you have your armor, you have your transport, and you're ready to catch your first bounty. You are fully trained in the art of bounty hunting. So I just want to end then by trying to replicate the atmosphere of a Star Wars planet. I want to give you the feeling of what it would be like to actually set foot on your first Star Wars planet, hunting your first bounty. So our last stop on our galaxy hopping trip is Hoth, the iconic planet from The Empire Strikes Back, an ice planet. Now, we've talked about taking humans and cells a little bit below zero, so where that gray arrow is. But what if we try and go not just a few degrees below zero, but almost 200 degrees below zero, negative 200 degrees Celsius, where nitrogen is a liquid. Now, why do we want to do this? Well, according to scientists, the real temperature of Hoth, rather than being the rather balmy negative 30 to negative 70, it's probably nearer negative 200 degrees Celsius. And this is mirrored in our own galaxy, where we find planets where it literally rains liquid nitrogen as the temperature falls below negative 200 degrees Celsius. And at these very low temperatures, nitrogen in its liquid form is so cold, if we try and pour some on the floor, so I have a small amount here, if I'm just going to pour it on the desk, you can see it skitters around on the surface of the desk and of the floor. And this is because the floor is so much hotter than the liquid nitrogen that the liquid doesn't actually touch the floor. It floats on its own vapor like a snow speeder or a speeder. And this is known as the Leidenfrost effect. So for my last demonstration, I want to transport you to Hoth, landing on your first Star Wars planet, of course, with the iconic lightsaber umbrella. So here we go. We're going to land on Hoth, where it literally rains liquid nitrogen. Guys, thank you so much for listening. I hope you have a very happy Star Wars day, and may the Force be with you.